and welcome to the second video of the Logic course. This week we'll be discussing formal arguments. Let's get started. So why do we use formal arguments? So far, we've only dealt with natural language arguments and what fallacies look like in them. However, testing validity in them is quite difficult due to their arbitrary and colloquial nature. Therefore, it's much easier to identify invalid arguments when they are written down in a more formal manner. So what is a formal argument? It is an argument that has the following structure. There are a finite number of premises followed by a single conclusion. So these over here, P1 dot 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 Pn, are the number of premises that we have, and C is a conclusion. What is a valid argument? In all the conclusions that we have, so what is a valid argument? In all the cases when all the premises are true and the conclusion is also true, it's known as a valid argument. And by true, it just means the value that has been assigned to the premises is true. It doesn't matter if it's true in the real world or not. For example, if I say something like, I am a car, that might not make sense in the real world. However, if the value that has been assigned to the premise is true, it is true. The second thing that makes an argument valid is if the conclusion is false, then at least one of the premises is false. These two together, these two bullet points, make the rules of validity. We can remember these two laws easily by saying that truth goes down and falsehood goes up. Or if all the premises are true, then the conclusion has to be true. If the conclusion is false, then at least one of the premises is false as well. One more thing we need to remember is an inference is valid if and only if there are no counterexamples. If there's no situation where one of these two laws is not followed, then it is known as a valid argument. If we can find even one situation where one of these laws is invalid, then the whole argument becomes invalid. Remember, truth goes down, falsehood goes up. If the premise is false, it does not mean that the conclusion is also false. Falsehood does not go down, and truth does not go up. Truth goes down, and falsehood goes up. Similarly, if the conclusion is true, it does not tell us anything about the truth value of the premises. What are argument schemas? There are different common types of valid argument structures. Common types of argument schemas are modus ponens, modus tollens, double negation elimination, disjunctive syllogism, and disjunction elimination. They're essentially common templates which we often use in arguments. Modus ponens is the first type of argument schema. There are two premises and the conclusion supports them. If A, then B, A, B. So now if A, then B, and A are premises and B is a conclusion. For example, if you jump from a roof, then you'll fly. Here, jump from a roof is A, and you'll fly is B. You will fly is the conclusion. So if A, then B, A happened, hence B has to happen. All right, let's do one practice question. Is the following argument an example of modus ponens? If A, then B, B, then A. Pause the video and think about it for a second. The answer is false. This isn't modus ponens because modus ponens' structure is if A, then B, A, then B. Here, however, B comes before an A, and that makes it an invalid argument. And this is actually an example of denying the antecedent. This is actually, this, however, this here actually is an example of affirming the consequent. This is not modus ponens, and it is invalid. Modus tollens is the second type of argument schema. It has a structure if A, then B, not B, not A. If you jump from a roof, you will fly. You didn't fly, so you didn't jump off a roof. Your jump from a roof is A, you will fly is B. You didn't fly is not B, hence not A is you didn't jump off a roof. Double negation elimination. This is the third type of argument schema. Not A, A. This is very simple and self-explanatory. For example, I did not commit the crime. I committed the crime. Here, there's one premise and one conclusion. Disjunctive syllogism, A or B or C dot 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 N, not A, not B, C. Whenever the word disjunctive is used in the name, that means that there's A, B, and C. As we noticed before with modus ponens and modus tollens, there was only A and B, and hence there was no disjunctive in the name. Disjunctive syllogism, however, has A, B, and C. For example, I am smart or funny or handsome. I'm not smart. I'm not handsome. I am funny. Your smart is A, funny is B, handsome is C. I am not smart is not A, I'm not handsome is not B, and I am funny is C. The next type of argument schema is disjunction elimination. This also has the name disjunction in it. Hence, it also has three terms, A, B, and C. A or B, if A, then C, if B, then C, C. For example, I drive a car or I don't drive a car. Here, I drive a car is A, I don't drive a car is B. If I drive a car, then I'm rich. If A, then C, I am rich is C. If B, then C. Hence, C is always the case because either A or B have to happen, and whenever they happen, C also happens. All right. So the questions on the test regarding argument schemas will be you'll be given a statement and you'll have to identify the argument schema that has been used. One important tip to remember is that disjunction in the name means that A, B, and C are used. Whenever there are three terms in the example, you should know that it's either disjunction elimination or disjunctive syllogism. When there's only one term, for example, A, then we know that it is double negation elimination because in that there was no B, there's only not A. If there are two terms used, then it's either modus ponens or modus tollens. Now, what is a sound argument? An argument can be valid, but it may not be sound because the information provided in the premises may not make sense. For an argument to be valid, it just has to be true in the sense that it has to have the value true. It doesn't really have to be true in the real world. However, if you want an argument to be sound, it has to be true in the real world and should have an assigned value true. Inference trees. They are complex argument trees with multiple conclusions rather than one. You have to use the validity rules we've mentioned, the rule 1 and 2, that truth goes down and falsehood goes up, to identify the truth values of the propositions. Before we start this, let's just talk about what propositions are. So propositions are essentially premises and conclusions. So over here, these three are the premises, and this is the conclusion. All of them are a proposition, right? So when we talk about propositions, we're essentially talking about premises and conclusion. A proposition can have a truth value of true or false. All right, now let's do one practice question. So the first thing we do is make three categories: true, false, and non-determined. So true, false, non-determined. Now, within true, we know that A is true, and we know that G is false. We don't know anything else, and we need to find those things. So let's start from the bottom up. We know that if the conclusion is false, then one of the premises has to be false as well. So it has to be either B, F, or E. Let's try with B. If B is false, then A has to be false as well because A is B's premise. But we know that that's not possible because we've been told that A is true. Hence, obviously, B has to be true as well because of the rules of validity state that if the premises are all true, then the conclusion has to be true as well. So let's write B over here. And we know that B can't be false. So it either has to be A or F. Let's make the assumption that F is the false one, right? So if F is false, and when we make assumptions, we make brackets. So for assumption one, we make the bracket and we put F inside it. So if F is false, then E has to be false because if the conclusion is false, then one of the premises has to be false. And here, one of the premises is the only premise is E. So it has to be false as well. So we know that E is false. So over here, either A or D have to be false. But we know that A is not false, so it has to be D. So D. Finally, we also know that if D is false, then either A, B, or C have to be false. Then we know that A is not false because we've written that here, and we know that B is not false if A is false. Hence, only C can be false, and that is the false value. So F, E, D, and C. Now let's make another assumption now that E is the false one. So if E is the false one, then all of these other terms are just as it is. So E, D, C. But we don't know anything about F, really, because falsehood does not go down. So if E is false, it doesn't tell us anything about F. F can be true or false. So we don't put that in the bracket. Now we have two brackets. And what we do is we take the terms that are common from both the brackets and we put them in the respective category. So here the terms E, D, C are common in both the brackets, so they remain. But F isn't, so it gets sent to the non-determined category. This is how you solve inference tree questions. Now we know all the truth values of all the propositions, except for F, of course. All right, so this is how you solve the inference tree questions on a step-by-step basis. First, you mark the true and false values. Secondly, you start from the bottom up and use the basic rules to make assumptions for each premise. Thirdly, write down the different assumptions in the brackets. And the last step is the propositions that are common in the brackets are put in the respective category, and the ones that are not common are put in the not determined category. Now let's talk about propositions versus premises and conclusions versus arguments. A proposition can be a premise or a conclusion. A proposition can be true or false. So premises and conclusions can be true or false, and hence they're types of propositions. An argument can't be true or false, it can be valid or invalid. Multiple propositions arranged in a particular order make an argument. And an argument can't be true or false, it can only be valid or invalid. And similarly, a proposition can't be valid or invalid, it can only be true or false. Here, P1 dot Pn are premises and C is a conclusion. They're both types of propositions. And all of them together in this particular manner arranged that there are n number of premises and one conclusion make an argument. And an argument is also known as an inference. So they use those words interchangeably. And it's very important to remember these terms because you don't want to get confused on the test. All right, let's talk about semantical notations. Different types of symbols are used to express the relationships of an arbitrary propositions with itself and other propositions. So we use the Greek letters phi, psi, and chi for arbitrary propositions. So there are the different types of semantical notations: classical negation, consistency, validity, invalidity, logical equivalence, and types of propositions include satisfiable, tautology, and contradictions. The first type of proposition is a contradiction. An arbitrary proposition phi is a contradiction if and only if phi is never true. That means that there is no situation in which phi is true at all. I'm in Amsterdam and in London at the same time. That can never be true. Hence, a proposition is considered to be a contradiction if it can never have the value true. The next type of proposition is a tautology. An arbitrary proposition phi is said to be a tautology if and only if phi is true in every situation. If I'm not dead, I'm alive. Types of propositions satisfiable. An arbitrary proposition phi is satisfiable if and only if phi can be true. That means that there is at least one situation that makes phi true. I live in London. That can be possible. It's not always true. It's not always false. It can be possible, and that makes a proposition satisfiable. All right, a classical negation flips the truth value of propositions. That is, if a proposition phi is true, then its negation, not phi, is false, and vice versa. Suppose phi is a tautology, its classical negation would be a contradiction, right? So if suppose phi has a value t, its classical negation would be f. So far we've learned the semantical notations for one proposition. So all of these semantical notations, satisfiability, tautology, contradiction, classical negation, all of them only require one proposition. Now we're going to map the relation between different propositions. Consistency is one such semantical notation. It requires two propositions, and it says that two propositions, phi and psi, are jointly satisfiable if and only if they can be both true together. That means that if there's some situation that makes both the propositions true, it is raining and it is windy, are both consistent, as it is possible for them to both happen together. It can rain and it can be windy, and it can be rainy and windy at the same time. However, it is raining and it is not raining are not consistent. They're both satisfiable because it can rain and it can not rain. However, it can't rain and not rain at the same time. Hence, they are not considered consistent, but they're both satisfiable. A set that is a collection of propositions chi is satisfiable if and only if there is some situation that makes every proposition in X true. So now consistency isn't just between two propositions, it can have multiple propositions. If there's one situation where they are all true, then it's considered to be consistent, right? So the next semantical notation is validity. To show validity, also known as logical consequence, we use this symbol right here. And what that symbol basically says is that the argument is valid. So when this is the format you write it in, P1 dot Pn, logical consequence, and chi, essentially means that if all the P are true, then chi has to be true as well. That's just the rules of validity. You can also, the way you say this is chi is a logical consequence of P1 dot Pn. The last semantical notation we'll talk about is invalidity, something that refutes the inference or statement. An inference is valid if and only if there are no counterexamples. An inference is invalid if and only if there's at least one counterexample. A counterexample for an inference A1 dot AN over C is a situation in which A1 dot AN are all true, but C is false. So if one of the situation is invalid, that means there's one situation where it does not follow the rules of validity. That one situation is known as a counterexample, and that one counterexample is enough to make the entire argument invalid. Lastly, we'll be talking about logical consequence. So when the two propositions are locked together in all possible cases, so no affirming the consequent is possible. B is a logical consequence of A, and A is a logical consequence of B. Only then A is known to be equivalent to B. And if two propositions are logically equivalent, then they can be replaced in an argument without hurting the validity of the argument. They have the same meaning. The Venn diagram is perfectly overlapping. It means that they have the same truth value in every situation. That means that they are either both true or both false in every situation. And in an argument, if you know that two propositions are logically equivalent, you can swap their places without really hurting the argument at all. So if phi is a premise and chi is a conclusion, then chi can also be the premise and phi is the conclusion, because like I said, you can replace them. Now here are some types of questions known as the updates questions. In these type of questions, you need to read the premise one by one and eliminate different choices. Only two cases are left in the end, and you need to make the conclusion based on those two scenarios that are possible. Let's do one practice question. Now here, we've been given these premises over here. You don't really need to read the upper part. All you need to do is know this. At least one of the three suspects shot Mr. Burns. That's the first premise. This is the second premise, B. C is the third premise, and D is the fourth premise. Using these premises, we need to eliminate the different options. So here are the different options. One means that the person is guilty, and zero means that they're innocent. So we know that at least one of the three suspects shot Mr. Burns. So this one, the last option, is false because here it says that none of them shot Mr. Burns. So it's considered impossible. Let's eliminate that now. The second one, the second premise says that if Bart shot Mr. Burns, then Liza didn't shoot him. So if Bart has a 1 next to his name, then Liza has to have a 0. So that means this one is out of question. This one is out of question. See, if Liza didn't shoot him, then Marge didn't shoot him either. If Liza is 0, then Marge also has to be 0. So this one is out of the question, and this one is also out of question. Sorry. Lastly, if Bart didn't shoot Mr. Burns, then Marge didn't shoot him either. So if Bart didn't shoot him, then Marge did not shoot him either. So that means your Bart has not shot Mr. Burns, but Marge has, so this one is out of question as well. So we only have two scenarios left now. Using these two scenarios, we need to come up with a conclusion. Is Bart guilty or innocent? Let's look back at our table. Bart can either be guilty or innocent, and we don't know. So we would call this as not determined. Is Liza guilty or innocent? Liza is definitely also, we don't know anything about Liza. So she could be guilty or innocent. So we would also say not determined. And lastly, is Marge innocent? Yes, Marge is innocent because both of these are zeros. Metatheorems. So these are the last type of questions that'll be asked on the test. And now we know the different semantical notations that exist, right? Validity, logical consequence, tautology, satisfiability, consistency, etc., etc. We have to now use these notations and the general laws of validity to create metatheorems, to find proofs, basically. For example, suppose phi 1 dot 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 phi n is a collection of premises and chi is a tautology. Is chi a logical consequence of phi 1 dot 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 phi n, right? Let's solve this question now. So what we've been told is that there's an argument, phi and chi, and we've been told that chi is a tautology. So here we've been given an argument and we've been told to prove whether this is a valid argument or not for any value of phi. The way we do that is actually by playing the devil's advocate. So we say that rather than trying to prove that this is valid, we try to prove that it's invalid. We try to find a counterexample, one possible situation where this whole argument does not follow the rules of validity, and that would make the whole argument invalid, and hence it would refute the assumption that it's valid. If we can't find a counterexample, then we have to admit that it's valid. So let's play the devil's advocate now. The way we do that is by testing multiple different values for phi. Phi can be either a contradiction or a tautology. Let's try to make it a tautology. If phi is a tautology, and chi, as we know, is already a tautology, is this a valid argument? Yes, because if all the premises are true, then the conclusion has to be true, is what the rules of validity state, which is true in this case because both of them are tautologies and they're both true. Now, let's try to make it a contradiction. If phi is a contradiction, is this argument still valid? Yes, because falsehood does not go down. So if phi is a contradiction, it doesn't tell us anything about the value of chi. Chi can be true or false. And in this case, it's a tautology, so it's true. And hence, it is a valid argument. So they're both true. And since they're both true, we couldn't find a counterexample to make this argument invalid. Hence, we need to admit that it is valid. And the answer is chi is a logical consequence of phi. This is how you solve metatheorem questions. Let's try to do another question. In this question, we have the same setup, but now we've been told that phi is a contradiction. And what we need to do is prove whether this is a valid argument for every value of chi or not. So again, we play the devil's advocate and we try to find a counterexample. If we can't find a counterexample, then this whole argument is valid. So dot cont. Let's try to make this a contradiction first. If chi is a contradiction, then phi has to be a contradiction as well, because if the conclusion is false, then then at least one of the premises has to be false. And in this case, there's only one premise, so it has to be false. So that is the case because phi is a contradiction. Hence, this argument is valid when chi is a contradiction. Let's try to make chi a tautology, right? If chi is a tautology, then then it doesn't really tell us anything about phi, right? Because like we said, truth goes down, it doesn't go up. So we wouldn't know anything about phi. Phi can be true or false. Hence, it being a contradiction does not really affect the validity of the argument. This argument would still be valid if chi is a tautology. Now, since both of them are valid, we couldn't find a counterexample, and hence, once again, chi is a logical consequence of phi. So here's the breakdown of how to solve these questions. In questions like these, make a claim first and try to be a devil's advocate and try to prove the opposite of your claim. If you couldn't find a counterexample, then the opposite of your claim was valid, and if you can't find a counterexample to it, then the opposite of your claim was not valid, and your claim is valid, right? That's what we basically did. All right, then. So that was it for today, guys. That was week 2. There was a lot of information there and a lot of questions regarding inference trees, metatheorems, update questions, and there's a lot to learn regarding the schemas and the semantical notations. This is the most important part of the module, and you should do a lot of practice questions, and that's the only way to do it. So here's the homework. Learn all the argument schemas and semantical notations. Practice inference tree questions, update questions, and metatheorem proofs from Sowieso. And if you have any doubts, send them to me at uzairhanure786@gmail.com. I will respond to them within 2 to 3 working days. And also, if you want to do more practice questions and you need a practice test, then email me and I'll send it to you. Thank you. Have a nice day.